Welcome to the lecture on planning for self-driving cars. Today we will have a look at different strategies a self-driving car needs in order to get from a start configuration A to a goal configuration B. We will then identify different challenges and try to tackle them with several approaches and solve this path planning problem in a hierarchical fashion. So this lecture is part of the course Techniques for Self-Driving Cars, also held by my colleagues. And let's get started. So this is the typical view from a self-driving car on a road. And today's question is, how do we get this green trajectory? So we want to get from our current position to a goal. And the goal might be somewhere outside this view. So we need to know which overall route do we need to take. Should we make a right turn here or go straight and then make the right turn? From the picture you can already see that we also need to take into account the different lanes. So there are lanes which are only allow a right lane change, or the lane on the left here only allows going straight. We need to take into account that there are traffic rules and traffic lights, other traffic participants. So a lot of things we actually need to take into account for that. So let's first consider the different conditions or requirements we have for the resulting path our planner should output. So the most important thing is that the trajectory is safe. So we want to have a safe trajectory without any dangerous situations or collisions. On top of that, the next important thing is that the route is legal. So we don't want to run red lights or cross a solid line which we are not allowed to cross. The next two important requirements on top are now more related with the passenger who is actually in the car and in the self-driving car, since the passenger should also feel safe. So the perceived safety is also an important factor. On top of that, we have the comfort. So we don't want to have very strong accelerations. The whole ride should feel smooth for the passenger. And then the part on top is the route efficiency, because otherwise we might not take the self-driving car if it just takes long detours and we don't reach the goal in time. So if we now connect these requirements to the path, we want to get from A to B in a path which is safe, physically feasible, smooth, fast, short, or also other user-defined requirements. And in this picture you can see a typical situation where the car wants to take a left turn and needs to take into account the different participants. Like in this case, there are cars on the right crossing the intersection, so we need to wait for our traffic signal to turn green and then watch out for other cars. But from this picture you can already see that for just a left lane or for a left turn, this might be easy. But if you think about a route which is from city A to city B, we cannot take everything into account and think about all the different situations that can occur. So in general, this path planning task gets more complex and more hard if we consider larger planning horizons. So the challenges we can identify are that the self-driving car needs to react to different events. So there are speed limits we need to account for, red lights we need to consider. There might be jaywalking, so people just running a red light and step on the street. So we need to have a sort of emergency braking rule. There are also other slower cars we want to overtake. We don't want to follow a slow car for 3 hours. So we can see that these challenges can be tackled with a specific way of planning or a way of performing the planning. So at first we identify that not all information is available at first. So while driving we might gather new information about the environment and we want to include this in the planned path. So this leads us to formulating this path planning in an online planning fashion. So we constantly update the best path we want to take based on these new observations. And then the second part is that not all information is needed for each decision. So if we just want to know the overall route, we don't need to know where a specific car is in the future, because we can deal with that when we reach the corresponding intersection. So this suggests, or this conclusion is that we formulate the path planning in a hierarchical fashion with different modules, and they only have several or different access to information in that case. Since the online planning is done by just updating the path based on the observations, we now focus on the hierarchical planning. So this is an overview of the different modules we have for the planning. And the general idea is to divide the overall or the big task of path planning into different sub-problems or sub-tasks. So the hierarchy is shown here from top to bottom. And at the top, we have a global planning which just defines the overall route. So it's like a satellite navigation system which tells us to now take the next turn left, follow this route or follow this road, and then take a turn right. The next level is the behavior planner, which accounts for different driving scenarios or situations with other traffic participants and handles these situations. The next step is the local planning, which actually computes the trajectory as an output and then accounts for dangerous situations or for other requirements we have, like a specific acceleration we don't want to exceed. And then finally we pass this trajectory to the controller. And in this case, in this lecture, we assume that the controller is now already given. So we have a low-level controller that takes the trajectory and outputs the corresponding control commands. So we will only focus on these three. And the hierarchy also defines the amount of information that is available to each planner and also the level of abstraction it has. So this is our overview for the lecture today. We'll cover the different planners during the course now. And the hierarchy is roughly defined by the abstraction, as I said, and also the update frequency. So the top level has a very high abstraction because we only consider the overall plan or the route, and we do not need to update it in a high frequent fashion. It's enough to plan the route once in advance and then update it if we, for example, see that a route is blocked and we cannot go there at all. The mid-level has a mid-abstraction level and a mid-frequency, so we also update it more frequently, but only if the overall driving scenario changes. If we, for example, move from an intersection to a highway scenario or to just a straight road we need to follow. And then the lowest abstraction level is the local planning part, which needs to be updated with a high frequency because there are many changes, dynamic obstacles that move, and we need to update this path way more often than the global overall path. So first, we now have a look at the global planning and look at the different inputs and outputs this module needs. So the input is the user-defined destination. So we need to know where the car wants to go or the passenger wants to go. And we also get a map of the road network. So we need to know how the road is looking like. And then the output should be a sequence of waypoints. But note that these waypoints, they do not need to be super fine or with the highest resolution. It's sufficient to know roughly to go from intersection 1 to intersection 2 and then move on. So it's only a rough list of waypoints. So I already mentioned this comparison. The global planning is similar to a satellite navigation system. So we assume that we know where we are and we know what the overall map looks like. And the goal is to find this list of waypoints with the minimum cost. So in advance, we need to specify what's the requirement the final path should have. So either a very short one or a fast one. So we can combine different costs and objectives in order to get the best path, which is then defined as the path with the minimum cost. As I said, this can be done offline in advance, just to have the overall route, and then is updated when new information comes in. So beside the already mentioned blocked road, it can also be a traffic jam or a new speed limit, which was not updated in the map. So in these cases, when new information comes in, we need to update it. So the maps we usually use here are high definition maps. And the idea is for the global planning to convert this map structure into a graph structure. And then we can apply different search techniques on this graph in order to get this optimal path in the end. So from robotics, you might know that a common approach is to discretize the world. So we discretize actions and also states. and then we get a grid and can move in the grid or plan in the grid. But since we now deal with self-driving cars, we can make use of the fact that we have high detailed information about roadmaps. So we, for example, know where intersections are, or we know whether a street is a one-way street or what the speed limit is. So this is the comparison. This is the already mentioned occupancy or the grid map, and where we have different discrete states and actions. And here is such a more topological map. So we discretize the world in topological elements. This is an example of a high definition map. So you can see that we have different lanes and also different colors, which indicate whether the lane is just a common road or intersection or part of a roundabout. And we also have information about the traffic lights or also traffic signs in here. The idea now is to generate a graph from this map. So we take a different map as an example, and you can see the red edges or the red path segments, and we now define the nodes on this map. So a node is just the start of the start of one segment and the end of the next one. So we divide all these segments and describe the transition between one segment to the other one as a node. So these are the blue dots you can see here. And they just represent a pose. So in the easiest way, just the position and orientation of the car. Then the already mentioned red lanes or segments are called edges of the graph, or we define these to be an edge. So they contain information about the length of taking this path from the one node to the other one. We can also encode information like a speed limit or what type of street is it. Is it now, as here, part of the intersection, or is it part of the straight driving road? So we can encode as many information as we need in order to later compute a cost from it. Here's a very simple example with 4 nodes. So we have the nodes 1, 2, and then 3 possible next nodes from the node 2. And in this case, we would build the graph like this. So from 1, you can get, so you could also go to this node here, but we only consider this this way here. So we can go from 1 to 2, and then there's a decision whether to then move to node 3 or node 4, depending on which lane you want to be in afterwards. What I already said about the update is now that in case we get a new information about the map due to a construction site like here or a blocked road, we can encode this information or update it in the corresponding edge. So in this case, this edge cost from 2 to 4 would become larger, which then tells us to maybe not take this path and prefer the way to the node 3, for example. Okay, so the overall goal is to find the best path from start to goal. So we want to do this with a very small and simple example on this graph now. Let's assume our car is here and we want to reach the goal. So in this case, it's very easy. We can already see there's a direct connection by taking the right turn here, and we are directly on the corresponding lane we want to be in. But in contrast to grid approaches, it can be sometimes not that intuitive what the best path will be. So in this case, the goal is here, but there's actually no direct connection, at least on this part of the map, from the start to the goal, which means that we need to take a large detour and somewhere use a roundabout or make a U-turn in order to reach this goal. So this is also the advantage of using the high definition maps, that we also know what are legal paths, because we cannot just drive on this intersection and then go in the other lane. It is not allowed. So this is sort of encoded in the high definition map. What we now do is we take this graph, convert it into a tree. I will explain why. And then we use tree search techniques you might already know from robotics in order to find this best path on the graph. So on a graph we can, on a graph like this on the left, we can move from node to node, resulting in a path. But in case we are in one of the nodes on the graph, we don't actually know where we are coming from. We don't know the path we have taken in order to reach the node. So that's why we can transform this graph into a tree where we start at the top or the root node, which is the current one, and then all the decisions we can take are new branches, such that one path in the graph is one unique path in this tree. So now we can, if we now locate ourselves in one of these subsequent nodes, we already know what is the sequence of nodes we have taken in order to reach this final node. And this makes it possible to use search techniques, tree search techniques, to find the best path from the start to the goal node. Okay, coming now to the tree search, we want to find the best path to our goal node. And there are different strategies to do this. So we will differentiate between the different strategies in terms of completeness. So that means if there is a solution, are we going to find it? There is the metric of, or the, we can also, or metric of optimality. Is the search algorithm optimal? So if you find a solution, is it really the best one or the optimal one? Or is it just one of many solutions but not the best? We can also look at the time consumption of an algorithm to see how much time does it need to find the solution, and also the memory consumption. So how many different paths do we need to remember until we find the best one? And the last two are very important in order to implement these techniques in practice, because we have hardware constraints, and also in the self-driving car scenario, we don't want to plan forever until we get the next step, or the best path. In general, we can also differentiate between uninformed and informed search. So for the uninformed search, we do not use any prior information about the goal. If we have this information, which is usually the case because we know our goal position, we can also formulate the search in as an informed search. So we make use of this prior information because we already know what the direction of the goal roughly is. And then we can define a heuristic, which is like a cost estimate, and then find the best solution faster. Okay, so let's first start with the uninformed search. So two very basic techniques are the breadth-first search and the depth-first search. In the depth-first search, you can see the search tree here. We start at the current node, at the top node again, and we will subsequently explore all the neighboring nodes. So the way this works is that you usually have a kind of list or a fringe, which is the open set of nodes which are not explored yet. And the way this is done is we look at the list, we check what node to explore next. We explore the node or look where this node is and check whether this is now the goal node. And if not, we continue with the search and then put all the subsequent nodes on the fringe or on this list, because then we want to explore them afterwards. And here in the breadth-first search, we will always explore all the closest nodes actually. So if you treat this as different levels of the search tree, we first explore the second, third, and fourth node here, and then go to the next level. So we assume the solution is close, and we just explore the next level. So this algorithm is complete because it will find the solution in case there is one. It is also optimal in cases the action costs are equal. So here we could just assume that the cost is 1 to go from one node to the other one. And it will be, in concerning time and space, the algorithm space scales with b to the power of d. So b is the branching factor and d is the goal depth, because we need to explore so many branches at each level, and then we need to reach the level d in order to find the solution. Another strategy is the depth-first search, which means that we do not explore all the lower the next levels, but we will first decide on one level and then try to go as deep as possible into the search tree. And in this case, for example, explore this all the way up to the last possible node 4. And then in this case, there's no next state from there. So only in this case, we go back and then go on to search in the other directions. In case of an infinite space, this is not complete. So Consider, for example, in the self-driving car scenario, that we search for a route, and in case we here use the depth first search, we might just drive around the block forever, because this is the deepest branch in the tree you can have, and you would only try to find a deeper path. So in this case, you don't find the solution, because in the graph example with the HD maps, we have these. We might have an infinite space because you can go in a circle as in a roundabout, or just drive around the block. The depth first search is also not optimal. So in case we find the solution, since we favored the deeper solutions, and if the solution cost is 1, or the steps, the cost from one node to the other one is 1, we just found the solution which is the farthest away, which is not necessarily the optimal one. Concerning time and space, this scales in time with branching factor to the power of the maximum tree depth, so it's usually slower than the breadth first search. But concerning memory or the space, it can be better, because we can forget a lot of paths and subtrees because we already explored them. So in here, for example, if you explored these and you move to this branch, you could forget the complete left half because you have explored it. So far we assume that the cost is equal for each transition from one node to the other one. We can also encode different costs here, edge costs, which I already mentioned previously in the maps. So not each path segment is equally long, so we might want to account for that. So here I want to introduce the cost-sensitive search. So now we also take into account different costs. The uniform just means that the expansion of nodes is treated uniformly, so we do not consider the different levels of nodes, but we now focus on the costs. So it's not like it's not that the costs are uniform, that's just the treatment of nodes concerning the level is uniformly. So we define a cost function, G, an accumulated cost function, which for each node keeps track of the cost which was needed to reach this node. And in this example, you see the different edge costs as a red number. So it's you can see that they are different. When starting at node number 1, for example, exploring node number 6 is not done in this case, because the cost is 7, which is higher than the other costs. So in this case, we prefer exploring node 2 with a cost of 2, and then move on to 3, because this has an accumulated cost of 3, which is still less than exploring this one with 7, this one with 5, or this one with accumulated cost of 6. So you just, on this fringe, or on the set, or the open set of nodes, you keep track on the nodes which are not explored yet, and this accumulated cost. And then you expand the one which has the lowest accumulated cost so far. This algorithm is complete and optimal, and scales, or the time and memory requirement scales with the C over E, which is an estimation of how many levels we need to explore in case the minimum edge cost is E and the solution cost is C. So it's a rough estimate of these requirements. As I said, the previous methods are uninformed search techniques, so they don't use any prior information. And now we want to make use of the fact that we know where the goal is. So now we want to guide the search a little bit to make the algorithm faster. So informed search techniques exploit additional knowledge about the goal. What is usually done is to define a heuristic, which is basically a cost estimate, and tells us what you expect the cost might be from this node to the final goal we want to reach. And this speeds up the search, as you will see soon. So one very easy implementation of this would be the greedy search, which means for each node which is not explored yet, you just take into account the estimate of future costs from this node to the goal. So you just look ahead. You don't consider the past costs. You just look what's for example, the node with the closest distance to the goal, and explore that. So this heuristic H describes, in this case, from node B, the estimated cost to node 12, so from 4 to 12. And this is the only thing we take into account for selecting the next node. And we, as I said, ignore the accumulated path cost. So this is important, since in the A star search, which is now a combination of uniform cost search and the greedy search, we take both into account. So now we consider the path cost, or the cost so far, which led to the corresponding node, and also the cost to go, which is an estimated cost to reach the goal. So we now combine our already defined accumulated path cost function and the heuristic, so G and H. In this case, again, we are at node, or we consider node 4. So we know what the cost from 1 to 4 was, which is given by the function G. And we have an estimate what the cost can be from 4 to 12, which is then given by the heuristic H. So here, what we do is we expand the next node with a minimized accumulated cost and estimated cost, so the sum of them, which is here. So this is then the F cost. Okay, so what does our heuristic, how does it need to look like? So we use this F function, which determines the overall cost based on the past cost, the accumulated cost G, and the heuristic H. And let's assume that H star is the actual cost from the node to the goal. So it's the real cost we will encounter in that case. And it's important that H is admissible. What does it mean? So the heuristic H is only allowed to underestimate the cost. So it needs to be equal to the real cost or lower. It may not be higher, because in that case the optimality is not guaranteed anymore, because then the heuristic might guide us to a suboptimal path, and we will reach the goal on that one and then think, okay, we are done, we found the path, but in this case it's not optimal. So for A star, we require that the heuristic H is admissible. And one example heuristic is, for example, is in the Euclidean space the direct distance. So if you are at a position, you could use the direct distance from the position to the goal, since this is always the minimum cost in this case. So you cannot, if you take a detour, it's already longer than the direct connection. So if you want to minimize for the path length, then this would be possible and very easy to implement. If you, for example, want to optimize it in terms of the travel time, you could use a similar heuristic. You take the smallest distance and the highest velocity you can achieve, and then compute the time required for the car to drive there. Because if you take another path which is longer, or a velocity which is slower, you will end up with a higher cost. So in this case, it's always an underestimation of it. Here's a small example of the A star search. So we start in this configuration space here at this position, and the goal is here. And you can see that here are obstacles, so we need to find a path around the obstacles. So you see in black the different nodes that have been explored. It's very fast. I will play it a couple of times, I guess. The light gray nodes are the ones which are not explored yet, so they are on this fringe, and we keep track of the cost that led to this node and also of the estimate to the goal. And the red one is always the one which is currently explored. And you see that due to the heuristic, we avoid exploring spaces like these, which are too far away from the goal. So whereas breadth first search would have explored these two because they are close to the start, or depth first search, which would have explored these because they are very far from the start, our A star accounts for the distance to the goal. And then at this point you see that there are two possible ways it has found, so going around the obstacle like this, or going there like this. And then since this one first reaches the goal, it's the optimal path which has been found. Okay, now we go to the second module, which is the behavior planning. So we got now from the first planning module, from the global planning, is the sequence of waypoints. And from our perception system, we also get the measurements from the surroundings, from the neighborhood. And the goal now is to output a rough maneuver, which specifies the behavior the car wants to perform now. So it can be making a full stop at an intersection, or driving straight, overtaking a car. So it's a rough description of many different possible outcomes, but it's the same scenario. We do this because we know that following the global path requires different maneuvers and behaviors depending on the current situation. And since we cannot know in advance what situation might occur, we need to keep track of all the possibilities our car could encounter. So this takes into account the interactions with different traffic participants and also stop signs, traffic rules, emergency stops, so all of these overall maneuvers. A common way to achieve this is defining these transitions and states in a finite state machine. So a finite state machine is described by a finite amount of possible states we can be in, and one state describes the scenario we want to tackle and the maneuver, and the transitions between the different states are based on the observation. So if something changes in our perception from the environment, we move to another state and then the car will behave differently. And one way to do it is in a very easy rule-based way to just say, if X holds, then do Y, or then go to state Y. I will now show a simple example. So here we have a finite state machine with 3 states. So the one state is that we are on a road and we have a reference speed according to our trajectory, and we want to follow this speed, this trajectory with the speed. Another maneuver or behavior could be that we have a lead vehicle in front and we need to adapt our velocity to the leading vehicle in order to not crash into it. The third possible state is overtaking. So if in case the car is then slow, we might want to overtake. So these are roughly the 3 possible behaviors you might have on a road. And let's now imagine we are in this state right now. So we have the trajectory, we follow it, and now we need to measure our environment and see what happens around us. So we stay in the state as long as these two transitions or conditions do not hold. So in case we detect a leading vehicle now and we detect oncoming traffic, we decide to follow the lead vehicle because we don't want to crash. So, and if there is a lead vehicle and we don't have traffic on the other lane, we can overtake. So in that case, we move to this maneuver. Let's now assume that this condition holds. So we now move to a different state, which describes follow the lead vehicle and adapt your speed to it. Now we again keep track of our surroundings and check whether the leading vehicle is still there. So in case it takes a turn somewhere, the path is, or the front of us is free again, so we can get back to our old velocity and follow the trajectory. In case the vehicle is still there, we then detect no oncoming traffic, so the other lane is free, we can then perform the overtaking maneuver, which we simulate now. So in this case, we do an overtaking, and now we still need to keep track of everything. So let's say we now detect an oncoming traffic. We need to fastly merge back to the old behavior and follow the vehicle. So merge back to the lane, abort this maneuver in order to not crash into the other car. Or if the lead vehicle is now gone, since we, for example, performed the overtaking maneuver, we can follow our old trajectory with the old speed again. So you see that these transitions between the states depend on other traffic participants. So we need to observe them and also estimate what they are going to do, since this affects our decision in that case. But the future behavior of other vehicles is of course not known usually, so we can just infer from the observations we do, and it's possible to support this decision making or to decide whether a transition between the states needs to be done now by predicting what the other participants might do. So in this picture you can see, it was already shown before with this left turn, that we now see different predictions for the cars. So first we detect different cars here with these bounding boxes, and then we predict what they might want to do. So we predict that this car is, for example, taking a right turn, so we don't need to let it pass. We can maybe roll forward and then make the left turn behind it. And these cars are, of course, driving straight or making a left turn, so we need to let them pass before. This behavior estimation is typically done based on different inputs. So one thing we can use is the set of past positions and velocities and accelerations. So if you know where the other cars have been and how fast they are, you can estimate where they might go. You can also use the map estimation or the map information. So if you know that the car is on a specific lane, which is only intended for left merging or taking a left turn, you would know that this car might do a left turn. Of course, it could still break the rule, but that's something which is really hard to model. So it's usually in that case assume that the cars follow the rules and do the left merge or lane change. We can also use different sensor data. So we have the car or the self-driving car equipped with camera, LiDAR, and radar systems. So we can also use this information to try to estimate what the cars might do in the future. And then common approaches to tackle this behavior estimation can be loosely grouped in physics-based, maneuver-based, and interaction-aware approaches. So in physics-based, we could, for example, use the past positions and forward integrate the velocities and accelerations. So if the car was going fast, we know that the next step it will be farther away. Maneuver-based approaches try to estimate the overall maneuver. So to estimate this car is performing a lane change on the highway or it's just driving straight. And then based on that, you can predict what the next steps will be or the next positions. Or you could model it in an interaction-aware approach or also a combination of these. But in this overview, I tackle them separately. So in the interaction-aware approach, we try to predict the behavior based on what the others do. So since in the driving scenario, everything is coupled and vehicles pay attention for each other, their future behavior heavily depends on each other. So yeah, and as I said, you can also use, of course, different combinations of it, and there's a broad variety of different estimation techniques. One important thing when it comes to behavior estimation is to account for the multimodal nature of this problem. So sometimes different future behaviors of cars are equally likely. So you cannot say whether the car is now going straight or going straight and then making a left turn. So you need to account for different possible outcomes. All right, so we now define the global planning, so we get the overall route. We know our current behavior based on the observation, so we know whether we want to follow the route or make the turn in the intersection or merge the lanes. So now we finally come to the local planning, which then outputs the desired trajectory. So that was our overall goal, want to output the trajectory, which is then passed to the controller. So the input here is the desired maneuver and also the measurements of the surroundings. So we know where we want to go, we know how we do it. So the behavior planning was more about how to follow this trajectory. And now we use this information to come up with the real path and the velocity profile. So now it can be or a path with a high resolution, which accounts for each time step where should the car be in the future. So the goal is to return the reference trajectory, which should be followed in a predefined horizon. Since we do not plan the whole path in such a detail, we usually take a specific horizon and only output the path for example, the next 5 seconds or the next 10 seconds. We also generate a velocity profile, which is based on the previous decisions in the behavior planner and also the speed limit from the map in the global planning. And of course, if we remember this pyramid from the beginning, the trajectory should be feasible, so the car should be actually capable of following the trajectory and should be obstacle-free, which makes it then safe. And a common approach to do this is to generate different trajectory candidates, to score them according to some objective. So we can include these conditions or these requirements in these objectives and then pass the trajectories to the controller, and then the one with the best score is actually followed. So first, as I said, we need to generate the path, and I now want to present different examples to do this. So one is to use a combinatorial planner. Here's an example. So we have different obstacles in green, and we try to find the path which does not interfere with the obstacles. So the output is already an obstacle-free path. which is good because we do not need to check again whether we hit an obstacle, but it can be intractable if we have a lot of obstacles in there and we need to account for some safety margins. And when it comes to dynamic obstacles, it gets really hard to already output the obstacle-free trajectory. Another way is a variational planner. So we propose an initial trajectory and then optimize this by checking small deviations from this first guess, and then optimize it with respect to obstacles or also the dynamics in order to not exceed specific accelerations, which might lead to an uncomfortable driving. The drawback here is that it can be slow to optimize it, and it might not converge. So in the end, we might still have a path which is non-optimal because it, for example, hits an obstacle or exceeds some acceleration we initially decided not to exceed. Other ways to generate the path is to use a sampling-based planner. So we just sample from the whole configuration space, sample these configurations and evaluate them. This is actually, in fact, fast and easy to implement because we know this configuration space. We just sample from there and then combine it to a path. But it is often suboptimal because we cannot explore the whole configuration space. It might have been better to be closer to these obstacles in order to make it faster. So it's just one way to achieve the goal, but maybe not the optimal one. And then especially when it comes to self-driving cars, we can also think about lattice-based planners because we know how the route looks like, or the road. So we can here account for the shape of the road and then propose trajectories which align with it. So which, for example, keep the current lane or perform the lane changes, and then you select from there. So they adapt to the road structure, but of course it's a limited action space because we do not think about each combination of steering, for example, but only in this case so in this case the velocity is sort of the same, or the acceleration. We just deviate we think about different steering angles in order to end up at different lateral offsets. So one way to generate this trajectory is to use parametric curves. So this is the contrast to sampling-based methods where we just sample configuration and combine the list of configurations. So here we have different conditions we need to meet, like the current position and the orientation and the final position orientation, and maybe also a constraint based on the curvature, because the curvature determines how nicely the following the trajectory actually is for the passenger. So this could be done by fitting a cubic spline or combining the different splines to a trajectory. So we define how the trajectory looks like in the parameter space. So we have different parameters, alpha and beta. And this U then defines where we are on this part of the trajectory. And the parameters can then be fitted to the initial conditions we have. As I said, after generating the trajectories, we need to score them. So we need to come up with some objective functions in order to select the best one. So different objectives can be what is the distance to our reference from the global planner. So we need to overall, of course, follow this planner and only deviate from this path if it's needed, if we need to overtake a car, for example. But then after that, we want to merge back into the center lane because that's the best way, or the common way of driving in that case. We can also rate or score the trajectories in terms of the control effort we need to follow it, or the curvature, which then is related to how nicely we can follow it. Also the collision, so in case we collide with another car, we should not take this. So in this example, with this path from A to B, we might favor the red one because it's shorter. The other one is taking detours, and it's also not that pleasant to drive here with a lot of lateral accelerations. And the goal is then to select the one with the lowest score, and the score is usually the sum of those different objectives. And we can also weight them. If, for example, the distance to the reference is more important than the control effort, we can score them differently or weight them differently, and also discount them. Since we say, okay, if we have a collision 10 seconds into the future, it's not that important because in 10 seconds the situation might change, and then it's still okay to follow this path for the first second, and then we replan anyway. So for the obstacles, so this is a very important goal we need to account for, or an important score, since this is actually the most important thing, that we do not crash into other cars. So we need to have an obstacle-free path. And from the view from the beginning, you can see that there are many different obstacles we might encounter. So in general, there are static and dynamic obstacles. So we have parked cars we should take into account, because they might just park on the road, so we need to go around. There are illegal lanes, so we are not allowed to cross this lane where the other cars are driving. We have sidewalks, so we need to take into account that we do not cross the sidewalks, because that's also not allowed and we might hit a pedestrian. Then we have also dynamic obstacles, like other vehicles that also drive around us, or pedestrians, which, as I said, can just step on the road, and then we should do an emergency brake in order to not collide with them. So the collision avoidance can be done roughly with two strategies. So one is this combinatorial planner that already generates collision-free trajectories. So we can make sure that the trajectory which is outputted is fine and does not collide with anything. Or that's the other way, we just generate the arbitrary trajectories, not taking the collisions into account, and then we check for collisions, which then influences the score we have. So usually we use safety margins. For example, we could just make the obstacles larger as they are, just to have a shot of safety here, a safety margin. But the problem is that the collision-free trajectory might not exist, especially for long planning horizons, or if you have a lot of obstacles or the dynamic obstacles. So this is why in this lecture we will focus on the second part, so this generating, scoring, and then passing the trajectories scheme. Here you can see different ways to check the collisions. So one very simple metric is the time to collision. So in case we have a leading vehicle, we just compare the different velocities of our car and the leading car, and then compute the time. So in case we keep these velocities, we compute the time which is then needed until or the time which has passed until we crash into the car. And then you can define a threshold and say, if this collision time to collision, is above a specific threshold, it is not important for us, because we can still change our behavior then. But if it's under a certain threshold, you need to act against it, because otherwise, in, for example, 5 seconds, there will be the crash with the leading car. Another way of checking for collisions in case you have the trajectory is the so-called swath computation, which can be done for occupancy grid maps, as in this example. So we have a grid map of our environment, and the trajectory here is from A to B with the car at A. What we do is we take this footprint of the car, so we know the dimensions of it, and we translate and rotate this footprint according to the reference trajectory. And then for each cell which is covered by this footprint, we can say that at some point in time, at a specific point in time, there will be a car there. And then in order to check a collision, we just take the other car and check which cells are occupied by this car, and then we can compare whether there is for a specific cell in the grid, whether there is a collision. Another way to encounter this is the circle collision checking. So we have two different cars here, and we approximate their dimensions by circles. So in this case, 3 circles are sufficient to cover the whole space the car is taking. And then we check for a collision by for each pair of these circles by comparing the distance between the two centers of the circles, and then there will be a collision if this distance is smaller than 2 times the radius in this case. So this is very efficient, because we just need the 3 circles and a couple of checks between them in order to say whether there will be a collision between these 2 cars at this specific time. Another way of scoring the trajectories is looking at the motion constraints we have. So from the pyramid, you remember that the perceived safety and also the the way how comfortable the trajectory is also important for a self-driving car, because the passenger should feel safe, and also it should be a pleasant ride. So from the bicycle model, we usually assume for the car motion, we can see that when steering, we move on a circle. So the curvature of this circle can be related to the acceleration the passenger is experiencing while driving. So when we look at this trajectory here, we can approximate these circles with the center of Stachniss curvature here, and the radius of the circle is inversely proportional to the curvature. And then from the curvature, we can compute the experienced lateral acceleration. And then we define a specific maximum acceleration, which is still okay for a passenger. And then you can see from this derivation, so the lateral acceleration is the velocity squared divided by the radius. So with this curvature definition, it's then c times the velocity squared, and this should be below this threshold. And you can see from here that we could now either reduce the curvature, so make the trajectory more straight, or just reduce the velocity in order to meet this condition. Another task of the local planner is to provide the velocity profile. Since this is now the last step of this whole hierarchy, it's in fact the last module before we pass it to the controller, and the controller just does what you tell him to do. So we will just follow the trajectory. So here we need to account the different velocities from which are set, or the velocity limits which are set from the other modules. So we might have a speed limit from the global planner, because you know from the map that there is a maximum speed limit. We might also have this constraint concerning the lateral acceleration from the previously discussed local planner, because we know we need to limit the curvature or limit the speed. And from the reference planner, we can also get a reference. If you, for example, switch into the state of braking, the velocity should be set to 0 as fast as possible, because we want to make a full stop in order to, let's say, not hit a pedestrian or another car. And then what you do is you take these different velocity limits and consider the minimum of it, because each of the planners says this is the minimum velocity or the maximum velocity we should have. And then you just take the minimum of it, which guarantees you that each planning module, each constraint from each planning module is met. And then one way is to do it in a linear ramp. So if v0 is our current velocity, and this is our now set velocity, so the minimum of these limits, then we just try to increase the velocity until we reach the final reference, and then we just keep it constant as long as we do not have another set velocity because the perception changes or anything like that. Okay, so now we came to an end. So we discussed all the different steps now which are needed to perform the path planning problem. You've seen that we defined the path planning in a hierarchical fashion by dividing the different tasks or the whole task into different subproblems, which have different access to information and consider the path planning with a different level of abstraction. So the global planning returns the optimal overall route with a given road network, so just the course sequence of waypoints we should follow. The behavior planner then takes into account the other traffic participants and considers traffic rules and socially compliant behavior when you let someone else pass first, for example. And then after that, we have the local planner, which finally computes the feasible trajectory and makes sure that it meets the requirements from the other planners, so that it actually this path is close to the global route, that you take into account the velocities given by the behavior planner if you want to make a full stop, for example. And then finally, the local planner checks for collisions and guarantees that the final trajectory meets all these requirements we defined before. And then you pass this to the control, and then the controller can follow it. And with this, we are done with the planning problem, and thank you for your attention.